Hello and good afternoon friends, welcome to CEC live lectures. Dear friends, in our previous session on chemistry, we discussed in detail on ultraviolet spectroscopy. Dear friends, we would be continuing further from where we left in the previous session and would be discussing more on ultraviolet spectroscopy. Not only ultraviolet spectroscopy would be covered, but we would be discussing in detail on nuclear magnetic resonance spectroscopy too. And for the discussion on the two spectroscopies, we have once again with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. Dr. Vandana has immense experience and she has contributed a lot in the area of academics. She has written various journals and she has also contributed to the various articles. Dear friends, through the live transmission of CEC, she continuously delivers lectures so that the student community is benefited as a whole. Dear friends, if you want to ask questions from Dr. Vandana on today's topic, then you can call right in the CEC studio. You can contact us through our toll-free number. Our number is 1800-110-430. Please write down the number once again. Our number is 1800-110-430. Friends, you are requested to call in the last 10 minutes of the lecture so that the lecture goes uninterrupted and your queries are also resolved in the last 10 minutes. That is what we believe. So let's welcome our guest Dr. Vandana and let's try to have a deep insight into the two spectroscopies as I have already told you. Hello ma'am, welcome to the lecture.
Hello ma'am, thank you so much for nice words. Hello viewers, we have started a series on natural product and spectroscopy and we have started spectroscopy in this session. You know what is a spectroscopy? It is nothing but an advanced technique to analyze or to identify the organic compounds. We have discussed in detail about the IR spectroscopy, that is infrared spectroscopy. We have discussed the preliminary part of UV visible spectroscopy, that is ultraviolet visible spectroscopy. For a recap, what is a spectroscopy? It is an interaction of the electromagnetic radiation with the organic matter. Electromagnetic radiations can be infrared, electromagnetic radiation can be ultraviolet, can be visible, and any one electromagnetic radiation which has to interact with the organic molecule. So, study of spectroscopy we have discussed, it was based on emission as well as absorption spectra. Emission spectra was produced by the emission of radiant energy by an excited atom, and absorption spectra by the absorption of radiations by a certain wavelength. We have discussed about this relation E is equal to Hc by lambda, or we can say E is equal to h nu. So we can see this electromagnetic radiations that you can see from gamma rays to radio waves. And what you observe here, over here from left to right, lambda increases, frequency decreases as well as energy decreases. So we can ask or we can discuss any electromagnetic radiation in terms of wavelength, in terms of frequency, in terms of energy. So we should always keep in mind the relation of energy with the wavelength, frequency and energy. And we can analyze the organic compound by various spectroscopy like ultraviolet visible spectroscopy. Why it is divided into categories? Because you know, if you want to analyze an organic compound, you cannot analyze every functional group by a single test. For a particular functional group you need to analyze, you have to do a particular test. Same here, there are different kind of spectroscopy which helps in analyzing. For example, ultraviolet visible spectroscopy helps us, as we have discussed in the last lecture, it helps us to identify the conjugation, especially the alkyl constituent and the extent of conjugation. In IR spectroscopy, we have discussed about the different functional groups. In nuclear magnetic resonance, we will discussing it today in details. And in coming lectures, we will also discuss the another part of spectroscopy, another category for spectroscopy, that is mass spectrometry. We have discussed about the basic fundamentals of UV visible spectroscopy. Now the more concepts are also there, like chromophore concept. What is chromophore? Chromophore was considered any system which is responsible for imparting color to the compound. All those compounds which absorb light of wavelength between 400 to 800 millimicron will appear colored to the human eye. Exact color depends upon the wavelength of light absorbed by a particular compound. For example, nitro compounds, if you are see, generally look like yellow in color, and nitro compounds is the chromophore which imparts yellow color to the organic compound. Similarly, aryl conjugated azo group is a chromophore for providing color to azo dyes. We have studied about azo dyes. It is defined as, in advance, any isolated covalently bonded group that shows a characteristic absorption in the ultraviolet or visible region of the electromagnetic radiation. The absorption occurs irrespective of the fact whether the color is produced or not. Some of the important chromophores are, for example, ethylenic, acetylene, carbonyls, acids, esters, nitrile group, and etc. A carbonyl group is an important chromophore, although the absorption of light by an isolated group cannot produce any color in ultraviolet visible spectroscopy. But if they are attached with the organic compound, they will impart a color to the organic molecule, not in an isolated group. Chromophore, there are two types of chromophores in which the group contains pi electrons and they undergo pi to pi star transitions. Such chromophore are ethylenes, acetylenes, etc. Chromophore which contain both pi electrons as well as non-bonding electrons. Such chromophores, for example, carbonyl group, such chromophore undergo two types of transitions. Number one, pi to pi star and non-bonding to pi star transitions. We have discussed in detail all these four types of transitions involved or responsible for ultraviolet visible spectroscopy. Examples of this type are carbonyls, nitriles, azo compounds, nitro compounds, etc. Simple conjugated chromophores such as dienes or alpha beta unsaturated ketones have high E maximum value, that is 10,000 to 20,000. The absorption with epsilon maximum value 1,000 to 10,000 shows an aromatic system. Here you can see different chromophore, their transitions responsible for this particular absorption, and the maximum absorption over here, epsilon maximum value, and the solvent involved in this chromophore. Here you can see this is ethylenic, acetylenic, and carbonyl. You can see because double bond is there, so pi to pi star transition will be there only, and value is approximately 175, and epsilon maximum will be 15,000. If you are seeing here, this is acetylenic bond. It involves again pi to pi star and value will be 196 and 2000 value will be for epsilon maximum. If you are observing this carbonyl group, you can see non-bonding to sigma star for first bond, pi to pi star and non-bonding to pi star. Three transitions involved for this particular chromophore, and you can see the relative values also 220, 160, 180, 285, and these are the relative epsilon maximum, and solvent here is hexane. Another chromophore are here, nitro group, this is acidic, this is azo and double bond N, this is amide group. Responsible transition you can see over here, pi to pi star as double bond is there between N and nitrogen. Also because of this oxygen there will be non-bonding to sigma pi star transition also, and here you can see this is carboxylic group, non-bonding to pi star, 204 value for absorption maxima. Azo group, here you can see non-bonding to pi star. For amide group, non-bonding to pi star, and these are the values, different values. When aromatic nucleus is substituted with groups which can extend the chromophore, the absorption occurs at still higher values of extinction coefficient. We have discussed epsilon maximum. The presence of a compound or a functional group can be confirmed by other spectroscopic techniques, that is from NMR, from mass spectroscopy also, and from IR specifically. All the compounds with the same functional group which absorb at the same wavelength will be nearly the same extinction coefficient. if the disturbing factors such as conjugation or the alkyl substituent or any other substituent are absent. We have discussed in detail while discussing about the IR spectroscopy. Now the next group is auxochrome. We have discussed about the chromophore. Same here. What is the difference between chromophore and auxochrome? And auxochrome also is any group which does not itself act as a chromophore, but whose presence brings about a shift of the absorption band towards the red end of the spectrum, that is towards the longer wavelength. The absorption at longer wavelength is due to the combination because of chromophore as well as auxochrome. And auxochrome hence can be said to as enhancing group. What enhancing? Color enhancing group. Auxochromic groups do not show characteristic absorption below 200 millimicron. Some common examples for auxochromic groups are OH hydroxyl group, OR alkoxy group, NH2 amino group, NHR substituted amine, NR2 another secondary substituted amine, and thiols SH, etc. The effect of auxochrome is due to its ability to extend the conjugation of what? Of a chromophore by sharing the non-bonding electrons. Thus, a new chromophore results which has a different value of lambda, that is absorption maximum, as well as for epsilon maximum, that is extinction coefficient. For example, benzene shows an absorption maximum at a value of 255 millimicron and the epsilon maximum is 203, whereas when this benzene when we calculated about aniline, that is NH2 group attached to benzene, so this NH2 group act as a auxochrome and it enhances the value lambda maximum. You can see over here this value 255 now extended to 280 millimicron, as well as the extinction coefficient, that is epsilon maximum, get increases from 203 to 1430. Hence amino group, it acts as an auxochrome over here because it extends the conjugation of benzene with the lone pair of electron present on the nitrogen atom. Now the absorption intensity shift. We are discussing here very important shifts. First shift is bathochromic shift. It is an effect by virtue of which the absorption maximum is shifted towards longer wavelength due to the presence of an auxochrome or by the change of the solvent. Such an absorption shift towards longer wavelength, and it is also known as a red shift or bathochromic shift. The non-bonding to pi star transition for carbonyl compounds experiences bathochromic shift when the polarity of the solvent is decreased. Another shift is here, hypsochromic shift. It is an effect by virtue of which the absorption maximum get decreases, or we can say shifted towards shorter wavelength. The absorption shifted towards shorter wavelength is called hypochromic shift. It may be caused by the removal of conjugation and also by changing the polarity of the solvent. In case of aniline, absorption maximum occurs at 280 millimicron because the pair of electrons on nitrogen atom of an amine is in conjugation with the pi bond system of the benzene ring in its acidic solutions. A blue shift is caused and absorption occurs at shorter wavelength. In an ion formed in acidic solution, the electron pair is no longer present and hence conjugation is removed. In acidic solution, because when this NH2 group now changes to NH3+, so no conjugation is there now, conjugation has been removed in acidic solution. The value gets changed. Another effect is hyperchromic shift. It is an effect due to which the intensity of the absorption maximum increases, or we can say epsilon maximum increases. For example, pyridine observed at 257 millimicron and epsilon maximum value 2750, it gets shifted to 262 millimicron, epsilon maximum value 3560 for 2-methyl pyridine, that is the value get increases. because the introduction of auxochrome usually increases intensity of the absorption. It is defined as an effect due to which the intensity of absorption maximum decreases, extinction coefficient decreases. This is called hypochromic shift, and it is due to the distortion of the geometry. For example, if you are observing biphenyl, it absorbs at 250 millimicron, epsilon maximum value 19,000, whereas for 2-methyl biphenyl, here you can see that there is an introduction of methyl group at position number 2. What happens here? The value get decreases and epsilon maximum value also decreases. This is due to the distortion in geometry caused by the methyl group in position number 2. Here you can see the overall summary of the shifts. You can see over here. This is the graph between E epsilon maximum as well as wavelength. You can see here you can see bathochromic shift. I have written also that it is due to the mainly due to the chromophoric effect, that is we can say auxochrome or chromophore effect, or you can say with the effect of conjugation. If conjugation is increases, you will observe the bathochromic shift. If you remove the conjugation, or we can say non-conjugated systems as compared to conjugated, it will the lambda maximum get decreases, and you can see this is the hypsochromic shift. Here also you can see if there is a auxochrome, presence of auxochrome, and the epsilon maximum increases, you can see you observe the hyperchromic shift. And if you introduce a group which distorts the geometry of a molecule, you will observe the hypochromic shift, but the lambda maximum will more or less same. Another rule, Woodward-Fisher rule for calculating absorption maximum in dienes. First rule is, longer the conjugated system, greater will be the lambda maximum. The intensity of each epsilon maximum also increases with increase in the length of chromophore. The conjugated polyene system appears colored to the naked eye if there are more than 5 double bonds in conjugation, and absorption occurs around or above 400 millimicron, that is within the visible region, that only they can appear to your naked eye. The presence of alkyl group on the double bond also causes bathochromic shift. We have discussed various types of double bonds in conjugations are alicyclic diene or diene contained in an open chain system, that is you can say butadiene. Homoannular conjugated double bond are the conjugated double bond present in the same ring. It is also called homodiene. Here you can see the example. This is the one homoannular conjugated double bond. It is another the example of homoannular conjugated double bond. Another conjugated double bond is heteroannular, that is conjugated double bond present within the different ring and not present in the same ring. Here as the example, it can be present like this and like this. You can observe in different ways. Exocyclic and endocyclic conjugated double bonds. Here you can see, because these two bonds are in conjugation, alternate single and double bond. This bond will be treated as endo and this bond will be treated as exo. Same here, this double bond which is present in B ring will be treated as exocyclic double bond for ring A, and here you can see contain two exocyclic, this double bond will be treated as exocyclic double bond for ring A, and this double bond will be treated as exocyclic double bond for ring B. So in this way you can calculate, you can identify the different kind of dienes. Woodward formulated certain empirical rules for calculating lambda maximum in case of dienes. These rules were later modified by Fisher in 1948. According to these rules, each type of diene has a certain fixed basic value, and the value of lambda maximum depends upon the number of alkyl substituent or ring residue on the double bond, and or the number of double bond which extend by conjugation, by the presence of polar groups such as chloro, bromo, this is alkoxy, this is SR, etc. The various rules for calculating the absorption maximum in case of diene are given in the table. Here you can observe the devoted part for a parent value for butadiene system. For conjugated diene it will be 217 millimicron. For acyclic triene the value will be the basic value we are discussing here, keep in mind, this is 245 millimicron. For homoannular conjugated diene the basic value will be 253. For heteroannular conjugated diene the basic value is 215, and moreover you can see for one alkyl substituent, for each alkyl substituent, or we can say for each ring residue the contribution from lambda maximum will be 5. For one exocyclic double bond, or we can say for each exocyclic double bond the contributing value from lambda maximum will be 5. For a single double bond that extends the conjugation, the contributory lambda maximum value will be 30 millimicron. These are the values which is given for different auxochrome. Here you can see for OR, that is alkoxy group, the contributing value from lambda maximum is plus 6 millimicron. For SR, R group, NER group, 30 millimicron. For Cl, Br, chloride, bromide ion, plus 5 millimicron. For secondary amines, plus 60 millimicron. This is, you can see, acetate group, and the contributory value is 0. And we are discussing here solvent, in case of solvent ethanol, and which kind of transition we are discussing here, pi to pi starred. This is the problem number 1. Calculate the absorption maximum in the ultraviolet spectrum of 2,4-hexadiene. And here you can see this is the structure of 2,4-hexadiene, 1, 2, 3, 4, 5, 6. 6-membered ring, and Y-diene because alternate single double bond are present. So there are 2 alkyl group on butadiene system. So the basic value we have discussed in table. For conjugated diene the value is 217. So 217 millimicron is the basic value, and we have discussed for each alkyl substituent the contribution towards lambda maximum is 5. So for 2 alkyl substituent the value get doubled. Now the calculated value comes out to be 227 millimicron, which is matched with the literature value. Another problem is here, calculate the absorption maximum in the ultraviolet spectrum of this kind of structure. First of all, you need to identify that it is a butadiene system, alternate single double bond. So the basic value will be 217. Again you can see here there are 2 alkyl group, or so value contributed towards here 10, as for 1 alkyl group the value is 5. Here you can also observe this double bond, and this is a cyclic system. So you can see this bond is treated as exocyclic double bond. The value contribution is 5. Here you can see another important thing, that is ring residue. So you need to identify carefully what is ring residue. In a butadiene system, if this double bond, you can see this is the double bond of a conjugated diene system. So this these bonds will be treated as 2 ring residue, right? So there are 2 ring residues, I have marked over here. So the contribution towards the lambda maximum is 10. For each ring residue there is a contribution by 5 value millimicron. So for 2 ring residue it get double, and this can be verified with the observed value, that is 242 millimicron. Another problem is here, calculate lambda maximum for this kind of, you can see this is the biphenyl. So it is an example of heteroannular diene. You can see this is a butadiene, alternate single double bond, and there are 4 ring residue on each double bond, 1 and 2, and same over here 1 and 2. So there are 4 ring residues. So values get 4 multiplied by 4, that is 20 millimicron, not micromilli, millimicron, and this is also the observed value is found to be 234 millimicron. So we have discussed about the ultraviolet visible spectroscopy We have discussed various transitions like sigma to sigma star, pi to pi star, non-bonding to pi star, non-bonding to sigma star. And we have discussed about the various shift, important shift, bathochromic shift, hypsochromic shift, hypochromic shift, hyperchromic shift. So with the help of ultraviolet visible spectroscopy, you have seen that we can detect in any aromatic compound the conjugation. What kind of conjugation is there? How many alkyl substituent are there? The presence of chromophore and the presence of auxochrome. We can observe all these things from the ultraviolet visible spectroscopy. So you need to follow the ultraviolet visible electromagnetic radiation on the organic compound, and you can observe the data and you can calculate the lambda maximum value for these compounds. Hope you understood this ultraviolet visible spectroscopy. In coming part of this lecture, we will discuss in detail about the NMR spectroscopy, that is nuclear magnetic resonance spectroscopy. Thank you. Hello friends, in the series of natural product and spectroscopy, we have started with the ultraviolet visible spectroscopy. We have discussed in detail how can you take the help of ultraviolet electromagnetic radiations to identify the kind of conjugation, the extension of conjugation, auxochrome, chromophore. We have discussed in detail about the IR spectroscopy. IR spectroscopy helps us to identify, to clarify the presence of functional group in a given organic compound. Here we are going to take another type of spectroscopic, that is NMR spectroscopic, which is very important spectroscopy, because nuclear magnetic resonance spectroscopy is a powerful analytical technique which helps us to identify the carbon-hydrogen framework within the molecule. Two types of NMR spectroscopy are generally used, that is Proton Nmr, or we can say HNMR, and 13C NMR, or we can say Carbon NMR. HNMR is used to determine the number of protons and the kind of protons in a molecule, right? And C13 NMR is used to determine the carbon skeleton of the molecule. The source of energy, as we have discussed, we have to interact a particular electromagnetic radiation with the compound, with the organic compound for a particular spectroscopy. So to observe to discuss about, or we can say to take the NMR spectrum, we have to take the radio waves electromagnetic radiations, which have long wavelength and thus low energy and low frequency, as we have discussed about the relation energy, difference of energy for the particular transition Hc by lambda or h nu. When low energy radio waves interact with a molecule, they can change the nuclear spins of some elements, including proton and carbon. Nucleus of a hydrogen atom behaves as a spinning bar magnet. Because, why it is so? Simple, because it possessed both kind of spin, electric spin as well as magnetic spin. Like any other spinning charged body, the nucleus of hydrogen atom also generates a magnetic field. And nuclear magnetic resonance involves interaction between oscillating magnetic field of the electromagnetic radiation and the magnetic energy released by hydrogen nucleus, or we can say another type of nuclei as we have discussed, carbon. And these are placed in an external static magnetic field. The sample absorbs electromagnetic radiations in radio wave region at different frequencies. Since absorption depends upon the type of protons or certain nuclei contained in this sample. Consider a spinning top. Over here you can see it also performs a slower waltz-like motion in which spinning axis, this is a spinning axis of the top, moves slowly around the vertical axis, and this is precessional motion, and the top is said to be precessional around the vertical axis of Earth gravitational field. The precession arises from the interaction of spin with the Earth's gravity acting vertically downward, and this is called gyroscopic motion. For a particle to absorb a photon, which photon? Radio waves photon. We are following the radio waves electromagnetic radiation on a molecule. The particle must first be in the same sort of uniform periodic motion, that is precessional motion. We have discussed that it is having a precessional motion around it, according to this, along with this vertical axis, that is around gravitational field. If the particular particle uniformly periodic moves, that is precessional at, this is frequency precession, and absorb energy, the energy for that particular particle will be E is equal to hc, h nu, and this nu is what? Nothing, this frequency is what? Processional frequency. The radiation frequency must exactly match the precession frequency. Here you can see E photon, that is energy of photon, is equal to the hc, h nu, and this nu is precessional motion and this nu is photon. These all must be equivalent in value. The precessional frequency may be defined as the number of revolutions per second made by a magnetic moment vector of the nucleus around the external field. Which nucleus? Hydrogen nucleus around the external field which we are applying over there. Alternatively, precessional frequency of the spinning bar magnet, that is nucleus, may be defined as equal to the frequency of electromagnetic radiations in megacycles per second necessary to induce a transition. Because we have already stated that is, if we fall a electromagnetic radiation on a particular compound, there is some kind of change. If we are talking about UV visible, if we are talking about NMR, now we are discussing about NMR. So there is a change in, you can see, alternately precessional frequency of spinning bar magnet may be a frequency in megacycles per second necessary to induce a transition from one spin state to another. All nuclei carry a charge, so possesses spin angular momentum. The momentum of the moment of the spin angular momentum is quantized. Only those nuclei which have a finite value of spin quantum number will precess along the axis of rotation and will be NMR active. So a spin quantum number, or we can say this value should be finite. When it is finite, how can we say? If spin quantum number, this is associated with the mass number and the atomic number of the nuclei. Simply, if the mass number and atomic number both for a particular nuclei both are odd number, then the spin quantum number will be finite. If mass number and atomic number for both the nuclei, for a single nuclei both values are even, then spin quantum number will be 0. that is NMR inactive. As for a NMR active, the spin quantum number should be a finite value. As we have discussed in IR also, the dipole moment should be a finite value. If dipole moment is 0, then the molecule, or we can say molecule, will be neutral towards infrared radiations. Same over here. If mass number and atomic number are even and odd respectively, that is mass number will be even and atomic number will be odd, then the spin quantum number will be finite, and you can say these nuclei will be NMR active. These will produce the NMR spectrum. These will not be neutral towards the radio waves. If a proton is placed in a magnetic field, then it starts precessing. That is a motion against the gravitational field at the top at a certain frequency in a radio wave region, and thus will be capable of taking up one or two orientation with respect to the axis of external field. And these orientation, one can be alignment or one can be against the field, with the field or against the field. Both the orientations are observed if there is a precessional motion. If a proton is precessing in the aligned orientation, if that is within the same, that is from the external field, it can pass on to the opposed orientation by absorbing energy, and from the higher energy opposed orientation, it again comes back to the lower energy, that is it will become now more stable. How? By losing energy. The transition from one energy state to the other transition state, that is from the same orientation and with the opposed orientation, when it comes, it is called flipping of proton. And the transition between the two energy states can be brought about by the absorption of a quantum of electromagnetic radiation in the radio wave region with the energy value of h nu. How it happens? If we irradiate the precessing nuclei with a beam of electromagnetic radiations of desired frequency, that is radio waves, then the lower energy nuclei will absorb it and move to the higher energy state. The precessing proton will absorb energy from the radio frequency source only if, it will not absorb every time. When it absorbs, only if the precessional frequency of the nuclei will be the exact same as the frequency of the falling electromagnetic radiation, that is radio frequency beam. And when the quantum energy of electromagnetic radiation matches, the energy difference between the two energy states at the field strength will be h naught. And when this occurs, nucleus and the radio frequency beam are now said to be in resonance. What we said, I want to repeat it. That is the processional frequency of a nuclei of a precessing proton when it becomes equal to the frequency of radio frequency beam. That is the magnetic radiation which you are falling for the spectrum. When both become exactly same, then only the nucleus and said to be in resonance. This is the condition of resonance. That is why this is called, and only then the spectrum observed for a particular nuclei or for a particular constituent of the organic compound. That is why we are calling it nuclear magnetic resonance. This technique consists in exposing the protons, placing the substance which you need to analyze in an organic molecule to a powerful field. The proton will precess at different frequencies because the protons are different. So all the proton cannot be precessed all frequencies, and this is the root cause for the generation of NMR spectrum. Now we irradiate these precessing protons with the steadily changing frequencies for promoting or flipping protons from the lower energy state to the higher energy state, and observe the frequencies at which absorption occur. It is generally, should I stop? It is generally more convenient to keep the radio frequency, because we can change radio frequency of a particular electromagnetic radiation as well as the strength of magnetic field But what is more convenient? It is generally more convenient to keep the radio frequency constant and the strength of magnetic field constantly varied. At some value of the field strength, the energy required to flip the protons matches the energy of radiation. At this value, absorption occurs and a signal is observed in the condition of resonance. That is the processional frequency of a nuclei and the frequency of the radio wave region. When they become exactly same, it is called the resonance condition, and there is a absorption of that particular energy, and absorption occurs and signal will be observed. This spectrum now is called nuclear magnetic resonance spectrum. It may be noted that all protons do not absorb at the same applied field, but absorption depends upon magnetic field which a particular proton feels. Clearly, the effective field strength is different for different sets of proton, or we can say as one of the sets of proton will have slightly different environment from any other set of protons. Thus, at a given radio frequency, let's talk about ethanol, CH3CH2OH. There are, at one carbon there are 3 proton, and another carbon there are 2 proton. At one oxygen there is a 1 proton. So these all kind of protons are in different environment. So they will absorb different kind of energy, they will resonate at different energy. This is the basic fundamental of nuclear magnetic resonance. Thus, at a given radio frequency, different protons, or we can say different sets of equivalent proton, will require slightly different applied field to produce the same effective field strength, which causes absorption. NMR spectrum, we measure applied field strength for each set of protons, and the absorption peaks are plotted. The number of signals at different applied field, because we are varying the applied field, we are having the constant frequency, and this is equal to the different sets of equivalent proton. Now the important terms over here, shielding and deshielding. When a molecule is placed in a magnetic field, we have talked about the nucleus, but now we are talking about the electrons as well, because we cannot isolate electrons from protons. So we cannot avoid the effect causes by the electron at the same time. We are discussing here these effects also only, and these are shielding and deshielding. When a molecule is placed in a magnetic field, its electrons are caused to circulate, and thus they also produce a magnetic field apart from the proton. That is why it is called secondary magnetic field, or we can say induced magnetic field. Rotation of electrons about the proton itself generates a field in such a way that at the proton it opposes the applied field, and thus the field felt by the proton is diminished, and the proton is said to be shielded. But if the induced field, that is secondary magnetic field, reinforce, or with this applied field, the proton feels a higher field strength, higher magnetic moment, then such a proton is said to be deshielded. Shielding shifts the absorption upfield, and deshielding shifts the absorption downfield to get an effective field strength necessary for absorption. Such shifts compared with a standard reference in the position of NMR absorption arise due to the shielding or deshielding are called chemical shift. We have to take over here a standard. With respect to that standard, we are discussing about the shifting of absorption in NMR. That is, we are taking over here reference as a TMS, that is tetramethylsilane. Due to the low electronegativity of silicon, the shielding of equivalent protons in tetramethylsilane is greater than most of the organic compound. That is why we are taking TMS as an. It is not measured in Gauss but measured in equivalent frequency unit, which is then divided by the frequency of spectrometer used. So we can see that both the values will be cancelled out, the frequency of the this and the frequency of the spectrophotometer and this frequency of the radio waves. So this will be cancelled out. Ultimately we have a value of delta. Protons with the same chemical shift are called equivalent protons, and with different values these are called non-equivalent protons. Delta, or we can compare these values with respect to delta. You can see the sign of delta or tau. Here you can see the scale. How can we use the chemical shift? This is the delta value, starts from here 0, 1, 2, 3, 4, 5 up to 10, and again you can see this is the you can say tau value. Two scales are related by this expression. If you want to calculate the tau value, you can calculate it by dividing the delta value from 10. And what is the delta value? You can see how can we calculate the frequency of sample minus the frequency of reference divided by the operating frequency in megacycles per second. So ultimately we get the delta value, no unit is there. Types of proton and chemical shift in parts per million. For example, you are looking over here cyclopropane. This is the cyclopropane, and the delta value, observe, we are not discussing in details about the proton over here right now. You will discuss in coming slides. Let's see first, only ignore the protons. We are just looking we are emphasis on the delta value and tau value. For cyclopropane, these are the values. For primary hydrogens, these are the values. Vinylinic, in this case will be vinylinic, acetylenic, aromatic 6 to 9.0, or tau value will be 4 to 1.0. For fluorides 4 to 4.5 and 6 to 5.5 tau value. Chlorides 3 to 4 in delta, and for tau 7 to 6. For alcohols, the value for delta is 3.4 to 4 and 6.6 to 6 for tau. This is for ethers, ROR 3.3 to 4, and tau value will be ranges from 6.7 to 6. Esters, RCOOR, you can see the value of delta 2.2 and 8 to 7.8. For acids 2 to 2.5, and tau value vary from 8 to 7.5. For aldehydic proton, the delta value varies from 9 to 10 and tau varies from 1 to 0. For hydroxy proton, the value of delta varies from 1 to 5.5 and tau value varies from 9 to 4.5. For phenolic proton or hydrogen, this proton we are talking about, values varies from 4 to 12 tau value, delta value, and tau value varies from 6 to -2. For enolic, you can see the values. This is the enol and this is carboxylic acid proton, and the values varies from 10.5 to 12 and 0.5 to -2, -0.5 to -2 values. So these are the various values by which you can identify the kind of proton present in the organic moiety. Another reference is here for NMR spectroscopy, that is 2,2-dimethyl 2-silapentane 5-sulfonate, and here you can see the shielding and deshielding because of the different molecules. You can see aliphatic, alcoholic, olefinic, aromatic, amides, acidic, anhydride, and this is the scale of tetramethylsilane. And you can also observe that if we goes from left to right towards TMS, there is a observation of shielded and the field will be high, magnetic field, applied magnetic field value will be high. And if we goes from this side, from this to this side, there is a observation of deshielding, that is for these particular kinds of groups we are talking about, and the applied magnetic field will be low in value. This is the instrumentation of nuclear magnetic resonance graphical representation. Here you can see these are the magnets, and this is the radio frequency source, and this is the sample tube in which you have to take the organic compound. This is the amplifier, recorder, spectrum, simple graphical representation. Nuclear magnetic resonance spectrophotometer makes use of a magnet, a radio frequency, a detector and an amplifier. The detection system is used to note that energy is being transferred from where? From radio frequency to the nucleus. The sample under investigation is taken in a glass tube which is placed between the pole faces of a magnet. A radio frequency source, let's say 60 megacycles per second, is made to fall. We have already discussed in the previous slides that we need to constant one thing, either the frequency of this radio waves region, or we can constant the value of applied magnetism, and we are making constant this value, that is radio frequency source, which was fall on the sample. Now it can be done by feeding energy into a coil wound around the sample tube. You have to wound a coil. A signal is detected if the nuclei in the sample resonates with the source, that is delta energy. For the transition, energy required to flip the proton is the same as that of the source. Energy is transferred from the source via nuclei to the detector coil, and the output from the detector can be fed to the cathode ray oscillograph or to a strip chart recorder after amplification. We have seen that this is the amplifier and this is the recorder, or we can see the spectrum can observe over here with the help of a recorder. Protons being in different electronic environment in a molecule cannot resonate exactly at this. For practical purposes, radio frequency source is held steady at the set frequency, and field strength is vary. We have to keep this value fixed value, and we are varying over here the field strength, applied field strength, by placing small electromagnet to the pole faces of the main magnet, by increasing the current flowing through these electromagnets. Here you can also see this is the superconducting magnet, and here you can see this is the sample tube, and the sample is dissolved in a solvent in thin NMR tube and placed in a magnetic field. Or here you can also see these are kind of representation. You have to apply a external magnet field with the help of these magnets. As the field strength increases, the precessional frequency of each proton increases. Up to when they will increase? I am talking about the frequency until there is a condition of, or there is a situation of resonance. What resonance? That is the precessional frequency matches with the frequency of radio waves, and this is the condition of resonance. And as a proton or a set of equivalent protons comes to resonance, the signal from the detector produces a peak on the chart paper with the help of amplifier, and the NMR spectrum consists of series of peaks that correspond to different applied field strength. And we can also say that each peak means a set of protons. A set of equivalent proton will give a single peak. And here you can see the instrumentation part. This is the superconducting magnet, and this is the NMR console. In the NMR probe, the sample is rotated in a magnetic field and irradiated with a short pulse of radio frequency radiation. And here you can see with the help of a software installed in a computer, you can see the NMR spectrum. So we have discussed about the different kind of shifts in UV visible spectrum, how the value changes, how the lambda maximum changes because of the presence or absence of chromophore or auxochrome. We have seen the different kind of diene, butadiene system. How can we calculate the lambda maximum value? How can we analyze the presence of conjugation in a particular organic molecule? And we have discussed about the IR spectroscopy. We can analyze easily the kind of function group present in a organic molecule. Then we have started the NMR spectroscopy. We have discussed till now only a few part about the NMR spectroscopy, that is what exactly is NMR, why we are saying this is NMR spectroscopy. And I have stated that with the help of NMR spectroscopy you can analyze the carbon skeleton, that is the type of carbon or present in a different molecule or in a single molecule with the different environment, as well as the type of protons or the different sets of proton you can analyze in NMR spectroscopy. I have discussed why it is called NMR spectroscopy, because the precessional motion of a nuclei, or we can say precessional frequency of a nuclei, has to come in resonance with the frequency of radio wave region, and this resonance brings about the absorption of that particular energy which is responsible for the NMR spectrum. And we will discuss in detail in the coming lectures how can it helps us to identify the type of protons, or we can say different types of equivalent protons. We will discuss in detail in coming lectures. Hope you understood and you can apply to analyze the organic molecule. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving precious inputs to the lecture where we studied more and more on spectroscopy. Dear friends, if you have any queries, then do write to us at info.cec@nic.in. This is our ID on which you can give your feedbacks as well as your suggestions for this particular lecture. And if you have any queries, your queries are welcome. We will try to give answers to your questions when next time Dr. Vandana visits our studio. The lecture is going to be uploaded on YouTube soon, as we have uploaded all the lectures pertaining to the natural products and spectroscopy for you on YouTube. Keep watching them and keep writing to us. Your inputs are precious for us. Dear friends, it's time to take your leave right now, but we would be meeting again tomorrow, and tomorrow at 10 in the morning we would be continuing with our series on music. We would be covering Rampur Gharana once again. So you are requested to be with us, and if you want to ask questions in our live sessions, you can contact us through our toll-free number. Our toll-free number is 1-800-110-430. This is the toll-free number through which you can ask your questions live from the experts available in the studio. So dear friends, today we are saying goodbye to you. We will be meeting tomorrow. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.
Thank you so much.